Okay, so now we're going to talk about forces in two dimensions, where we look at forces that are acting not only in one direction but two. So as we explore this, in this case we've got a boat, and this is a top-down view, so we can draw the boat in the water. And we have four forces. We have a force to the right, a force to the left, a force up, and then a force down. So we can draw these forces as close as we can to scale. So 15 newtons to the right, 10 newtons to the left, 5 newtons up, and 22 down. And what we want to find out is the resultant force. So as we consider that, and this is a top-down view, we can set up our coordinate axis, positive x, positive y, negative y, and we can place our values there. So for the one to the right here, 15 newtons, is a positive force to the right, and then the 10 newtons to the left would be negative 10 newtons to the left. And then we have 5 newtons up, positive 5 newtons up, and then negative 22 newtons down. And so what we're going to do is we're going to get the total y forces, and another symbol for that, that's the sum of the forces of the net force in the y. And we can do that. We can get all the forces, and so we have the positive 5 newtons plus the negative 22 newtons, and we end up getting negative 17 newtons for that. And then we can do the total x forces, which would be the net force in the x, equals positive 15 plus negative 10, and we would have a net force of positive 5 newtons. So what we have is we have the total force in the y, total force in the x, and we want to find the resultant. So what we're going to do is we're going to do vector addition. We draw a new coordinate axis, and then we can draw our forces, 5 newtons, positive 5 newtons this way, and then 17 newtons downwards. And the resultant is going to be from the origin to here, and that's what we want to find, is what is this, how many newtons, and then blank blank degrees, blank of blank. So why don't you pause the video and go ahead and determine what the resultant net force is, and then you can continue. Okay, so you should have gotten 17.73 newtons at 73.6 degrees south of east. And the angle we can find using inverse tangent opposite 17 newtons over the adjacent. Okay, for the next one, we're going to look at a kite that has an upward force. So let's go ahead and draw a kite, and we can draw the forces on the kite. We have a lift force of 12 newtons. And we have a force of gravity of 7 newtons. We should really list these as variables, so force of lift, force of gravity.
Please report to the Media Center textbook room to pick up your PSAT
and
material. Mrs. Wallace, Mrs. Willis.
We've got the force of gravity, which is 7 newtons down here, which will be a negative, and we'll talk about that. And then we've got a force from the left to the right, so force of the wind. So what we're going to do is we set this one up, we're going to actually set it up in variable form. So let's get the net force in the y equals ma in the y, and in this case, you know, positive y, negative y, positive x, negative x. So we have the positive force of lift plus the negative force of gravity equals ma in the y. And so in this case, the force of lift, positive 12 newtons plus, and you can see how we have the negative in here already. We don't want two negatives, that's why I didn't put the negative down here. 7 newtons. And we're going to get the net force, which in this case would be positive 5 newtons in the y. And we can get the net force in the x equals ma in the x. And so there's only one force in the x, positive force of the wind equals ma in the x. So we have positive 3 newtons as our x force. And so we're going to do the same thing. Draw a coordinate axis. And we can we can draw out our forces on here and determine the force. And then in this case, we're going to distinguish this blank newtons, blank degrees, and then in reference to the coordinate axis, because really north is in the sky here, and south is in the ground. So it's better to distinguish it on the coordinate axis. So go ahead and pause the clip, and you can give this a try. Okay, so let's see how you did here. We have the 3 newtons down here, 5 newtons going here. So inverse tangent, we should get 59.04 degrees, 5.83 newtons above the x-axis. So instead of saying north of east, we can reference things based on the coordinate axis if that's more applicable. Okay, so the next question is, if the kite's mass is 0.71 kilograms, what is the acceleration of this kite? So go ahead and pause the clip and see if you can determine the acceleration based on the force that we have here in the mass. Okay, so we should have gotten 8.21 meters per second squared. We know the force, we know the mass, and we can find the acceleration. And this is part of Newton's second law, where we talked about how the acceleration is in the same direction. Acceleration is in the same direction as the force. And so the net force is this direction, so the acceleration must be in that direction. Okay, so for this sample problem, we want to look at how we can use the data from this graph to interpret force and displacement. So in the y-axis here we have force, and then we have displacement in the x-axis. And so the first question we want to ask is, at 10 meters, if this object is at 10 meters, what is the acceleration? And so this graph is different than the ones that we've looked at in the past, because this just tells us where's the object located and how much force is on it. And so this is not a motion graph. This is telling us how much force over a certain displacement. So we know the mass is 25 kilograms. We can come up here and find out what the force is. The force is 100 newtons. So F equals ma. We know 100 newtons of force. We have 25 kilograms as the mass. So the acceleration would therefore be 4 meters per second squared. So whatever this object is, that's the acceleration of it. The change in displacement to the constant force. So yeah, so let's say, during this time period there's a constant force of 100 newtons. We could say this is, on a cart, and we're pushing this cart with 100 newtons of net force and making it, in this case we're making it go faster. There's an acceleration. But this is pretty easy. It's just the displacement here from 0 to 20 meters. So over that 20 meters, there's a constant force. And then the next one, how much time does it take to go from, we'll say from 0 meters to 20 meters? And we'll assume that it starts from rest. So the initial velocity is 0. So if that's true, we know what the acceleration is. We know the initial velocity. So, and we know the displacement, delta x, and we want to find out how much time does it take for that to happen. So what you're going to want to do is go to your equation sheet and look under one-dimensional motion and pick out one of the 3 constant acceleration equations that will give you time. And in this case, we've got x final equals x initial plus the initial times time plus 1/2 at squared. And The final position would be 20 meters. The initial position would be 0 meters. The initial velocity would be 0 meters per second, so 0 times 0, and then plus 1/2 times 4 meters per second squared times time squared, and we're going to solve for time. And so we can multiply 4 times 1/2, that would be 2, divide both sides by 2, so 20 divided by 2 would be 10, so the square root of 10 is 3.16 seconds. And so, yeah, that's how much time it would take for the object to go from 0 meters to 20 meters. And so this is a different kind of problem because we're looking at it in terms of giving certain pieces of information, force and displacement. So as we recap a little bit, with the first law, the body in motion will stay in motion at constant velocity, and body at rest will stay at rest unless acted upon by a net force, an unbalanced force. This is the law of inertia. The second law, body will accelerate when acted upon by a net external force, and it will be in that same direction as that force, and then acceleration is directly proportional to the net force. So you double force, you're going to double the acceleration of the car, triple and triple. And the way we define the unit of force is a Newton. A Newton is the force required to accelerate 1 kilogram of mass at a rate of 1 meters per second squared. So if we had, let's say, 1 kilogram mass here, and it was frictionless surface, and we applied 1 Newton to it, it's going to get faster and faster at a rate of 1 meters per second squared.